Let's start on lecture 13. This lecture is going to focus on conditional execution. Due to the time limit, I will just skip some of the reviews of the instructions we talked about 20 minutes ago. So let's get directly into this compare instruction. Compare instruction compares two values, and it will store the result in flag registers. Flag register. It will use zero flag and sign flag. The general format of the compare instruction is CMP, stands for compare, destination, comma, source. The operation of this instruction is actually a subtraction, but without storing the difference of these two numbers. It will subtract S from subtract source from the destination, so D minus S. Destination and source unchanged. So it's different from the actual subtraction instruction where you will change the destination operand. But compare instruction will not change source operand or destination operand. Instead, it will update zero flag and the sign flag, which will be used to indicate the result. When we do the subtraction, we know that the difference is going to be a sign value. So it could be a positive number, could be a zero, could be a negative number. So if it's a positive number, we know that D is greater than S, destination is larger than source. If it's zero, then these two numbers are equal. And if it is a negative number, that means the destination is less than source. The overflow flag is taken into consideration because there are cases the subtraction actually will generate a value that's out of the range for the registers to hold. So we actually check whether there's overflow, and that's going to be in combination with checking the sign flag. So we have three scenarios. Zero flag is 1, that means the destination has the same value as the source. If the zero flag is a 0, and if sign flag XOR with the overflow flag is a 1, that means the destination is less than source. And the third case is when the destination has a value that is larger than the value in source operand. Let's look at an example. We have three instructions, two move instructions to initialize the values in AX and BX, and we then have a comparison instruction, CMP AX, comma BX. So after the first two instructions, we now have 1, 2, 3, 4 in AX and ABCD in BX. And what we are doing here is a subtraction. We're going to subtract BX from AX, and AX is this value 1, 2, 3, 4. BX has ABCD, and these two numbers are treated as sign numbers when we do the subtraction. So what you can imagine here, the AX has a positive number, and BX has a negative number because the sign bit of BX is a 1. So when you do the subtraction, or even before you do the subtraction, you know AX is larger than BX. But how does the computer know about this, and how will that information get passed on to the following instructions, later instructions? It is the comparison instruction who does that. Comparison instruction will perform this subtraction operation without changing the values of AX and BX. It will update the flag bits, in particular the sign bit and 0 bit, or sign flag and 0 flag. In this case, 0 flag will be a 0. That's indicating that the difference of these two numbers are not 0. And the sign flag will be a 0, indicating that the difference or the difference between destination and source is a positive number. And also the overflow flag is a 0, indicating there's no overflow. So combining these 0 flag, sign flag, and the overflow flag together, and following the previous 3 scenario criteria, we know that the destination operand indeed has a larger value than the source operand. Okay, so next thing we want to talk about is the condition codes. Condition codes, in fact, refers to a group of codes that representing the relationships or the conditions between two numbers. And the result of these conditions depends on the computation or the completion of the previous instruction. And the following instructions, oftentimes a conditional instruction like conditional branch, will perform corresponding operations depending on the actual condition. Intel instructions specify condition codes, and these condition code implies certain flag values. And we use uppercodes written as CC, this lowercase cc. The italic font is just a placeholder where you will actually replace the CC with the actual condition code. That's what it says here. CC can be replaced by any valid code. For example, we have cmove CC, set CC, jcc. These CC, again, are just a placeholder which should be replaced by the actual condition code. Now, what are the condition code? For example, E, which stands for equal, L stands for less than, and Z stands for 0, NE stands for not equal, and G stands for greater than. So these are the actual condition codes will replace CC in those instructions. We have some examples here. Testing overflow will use OV. If it's O, that means the overflow flag is a 1, or if it's NO, it means overflow flag is a 0. To test the carry flag, we use C or NC. C or NC both are condition codes, and you can use these condition codes together with other letters to make an instruction mnemonic or the upper code of the instruction. Similarly, we have sign flag S. That's when the sign flag is 1, or NS, the sign flag is 0, or parity flag, etc. And we have E or NE or NZ or Z. These are related to 0 result or equality result. Z or E, those representing the 0 flag is a 1, means the two numbers are equal. And we have signed comparison larger than, not larger, less than or not greater or equal. And we have not less than, or that means greater or equal, and so on. We also have unsigned comparison, for example, below or not, above or equal, and these set of upper codes for unsigned comparisons. You don't have to remember these condition codes or their corresponding flag bits. We will provide you a list if you will be later tested on the exam to use these condition codes. new instruction that uses such condition codes is the C move. This is the newer instruction that is only available in Pentium Pro or later. It performs move operation or data transfer operations only if a condition is true. For example, first instruction C move Z. Z stands for 0 or equal. Essentially, this move instruction will perform this data transfer if such condition is met. What condition? The condition is when the 0 flag is a 1. That's the condition. So this data transfer operation will happen only if the 0 flag is a 1. Next example is C move G. G stands for greater than. So this instruction will copy the value from EAX to EBX if the value, in fact, if the previous instruction, the comparison instruction, which usually will be the case, reveal that one number is greater than the other one. Byte set on condition instruction. Byte set. So this instruction is going to set a byte. What do we mean by set a byte? Make all the bits in a byte to be 1. That's what we mean by byte set. Byte set on condition instruction is used to set byte based on condition code. It can be used for Boolean results. For example, we'll see in the next slide. But before we look at the example, the general format is set CC destination operand. CC is one of the supported conditional relationships. For example, Z or NZ, C or NO, so those other condition codes can be used together or replace the CC. The result is going to set, I believe this should be FF here. If the condition is true, we're going to set the byte to be all 1. And if the condition is not true, then we're going to set 0 to be the condition. And set 0 to be the destination. Put 0 into the destination operand. The operation of this byte set is that the flags tested for condition defined by CC and the destination in the register or memory is going to be updated as follows. If the condition is true, we're going to put 1s into the destination. If the condition is false, we're going to put 0 into the destination. And here are some examples. Now look at these 3 examples. Set E, set C, set BE. So the first 3 letters are the same, SET, and the lowercase cc that you saw in the previous slide is now replaced with the actual condition code. And we have E, that means equal, and C means whether the carry flag is 0 or 1, and the BE is for the below or equal, for the unsigned comparison. And these are the flags that will be checked when these instructions are executed. For example, set E will check the 0 flag, and set C will check whether the carry flag is a 1 or not.
So this is something that's used after one of the other instructions, or can you do something and then you check and see what the flag is?
Yep. So these are the condition instructions that we talk about. So these instructions are often used after a comparison instruction, because comparison will perform the subtraction, will update the flags, so that later following condition instructions like these ones will be able to use these condition code. there are other conditional instructions, for example, conditional branch instructions, and that's the another use case of compare instructions. So we're going to compare two values, and depending on the result, we'll do a conditional jump. So we're going to either execute this part of the code or execute the other branch of the instructions. Exactly. So the conditional branch instructions are the actual assembly code will be generated when the compiler looks at your if then else in your high-level language programs. Okay, we have here some examples. We assume such values are stored in memory. We have these variables, A, B, C, D, E, F. These are, you can think about these as the variables in your C program. And when they put into memory, they will put in certain memory locations. And let's assume that they are in these locations. And each variable here is a 16-bit variable. So we have their initial values. Initial value of A, variable A, is 0001. And for B, the initial value is 3. And then for C, you have the initial value 1011, and so on. And then we have a list of instructions. And we assume these instructions are part of the program sequence. So these instructions are going to be executed one after another, and their result will affect later instructions. So let's see what these instructions will do. Maybe I'll give you 1 minute to think about. The hint I want to give you is that these instructions are trying to check a very complex condition among these 6 variables. By that I mean it's going to check whether, for example, A is less than B or not, and if that's the case, it will check whether what is the relationship between C and D, and so on. I'll give you 1 minute to try to figure out this. Okay, let me walk you through this example. Move AX comma bracket 100H. You can think about that we are trying to load the value from memory at DS 100. So we're trying to load this value of variable A into AX register. Right? So before we execute the second instruction, we now have AX, the value of variable A in AX. And then we do comparison AX comma this bracket 102H. You know DS102H has the value of variable B. So this comparison instruction will do variable A minus variable B. Right? Because subtraction, I mean comparison instruction subtract source from destination. So we're trying to do A minus B. I'm talking about variable A and variable B.
Source minus destination.
No, destination minus source. Subtract source from destination. So that's destination minus source. So we do A minus B, and we will set BL if it is less than.
So A is less than B.
You can just ignore the actual value for a moment. So we're going to do A minus B. And A minus B. And we're going to set L, E, B, L. So what we're trying to say is if A is less than or equal to B, that's where this is true, right? Less than or equal. If A is less than or equal to B, we're going to set BL. So that's the first three instructions. The first three instructions will basically do this operation if we think about it as a C high-level language code. Trying to do this check and to set BL.
What are you doing in this that equal to B? And not B less than A.
Because it's A minus B.
Because that's the previous instruction.
Comparison will do A minus B.
Yeah.
So we're talking about whether A is less than B.
Set the instruction set depends on the previous.
Yeah, exactly. So the set LE, this is a conditional instruction or condition instruction, and it will use the flags set or cleared by the previous instruction, which is the comparison instruction. All good? Okay, so let's move on to the fourth instruction. Move AX comma bracket 104. That is to put the value of variable C into AX. And then we do a comparison AX comma bracket 106. So we know we're doing C minus E. And we're gonna set E BH. So we're going to say if this E stands for equal. So if C is equal to D, we're gonna set BH.
How do we know what is BH and BL?
That's part of the instruction. Oh, you mean the initial values of them? We don't care because we just use them, and they are okay. For this third instruction, it's set LE BL. So BL is the destination operand. So if the condition is true, we'll set that BL, which means yeah, the BL will be FF. And similarly, when we check C and D, what we're doing here is we'll check if C is equal to D or not. If that's true, we're going to set BH. Why BH? Because the instruction here is set E BH. And then the seventh instruction, we have a and BL BH. And is going to do the bitwise logical and the destination is BL. So we are doing this BL and with BH. Really, the final value, or after this instruction, the value in BL depends on these two, checking, condition checking. If both of these conditions are true, then both BL and BH are going to be FF. And when you do an AND operation, BL will have FF.
And then we have to set command. So if it's not true, then it's set to 0.
Right. So if any one of these two, either of these conditions is not true, then you have 0 on BL or BH. Then the AND operation will give you a 0.
So if they are true, then everything, all bits except for 1 and BL, would be FF. In contrast to the previous slide, where it showed a hex value of 1.
Yeah, so I think that's incorrect to be FF. So if you go through the whole program, you will notice that it doesn't really matter. What we're doing is doing the logical operations. BL will have a new value after this AND operation. But this value in BL really tells us whether these conditions are true or not. Whether both of them are true or only one of them are true. Because when BL has FF, that's only possible when both of these conditions are true.
We don't need that operation to show that they are true. We can check that without the AND operation.
Which operation you're talking about?
You said AND shows that the previous instruction
Okay.
was true or not.
Yeah, hold on a second. You're saying this AND operation, this AND instruction is not necessary. But we'll see when we look at the last 4 instructions, you know this is actually necessary. Let's move on to the next instruction. Move AX, comma 108. So this instruction will put the value of E to AX, and then we do comparison. So this is to do E minus F. Right? So we're trying to do E minus F. And after that, we do set NE BH. We do a subtraction, we'll set NE BH. So what we are doing is checking E and F. If they're not equal, we will set BH. So these 3 instructions, we're trying to perform this operation. It's going to check whether E is equal to F or not. If they are not equal, it will set BH. So the value in BH is indication of the equality relationship between E and F. And the final instruction is or B L So back to your comment that this AND instruction will put the result into BL, and that result indicates the first two condition checking. And this BL will be used in the very last instruction is OR. This is actually going to say we will do a logic OR two logical or condition checkings. This one and the first two as a combination. Because this BL right here, this AND operation, will tell you the combination of these first two conditions. And this BH will tell you this third condition checking, whether it's equal or not. And then eventually this OR will combine these two groups. So what we are checking, the conditions, the relationship among these conditions is actually here as shown in this slide. We are checking first whether A is less than B or not, and we also will check whether C is equal to D or not. And we'll do an operation on these two conditions. So that's the logical AND. And the third condition we check is the equality between E and F. And we are looking for not equal. And after that, we'll do a logical OR on these